Hi everyone. I wanted to thank you all for joining me to watch this pre-recorded presentation for the Florida Remediation Conference. I'm going to speak about using 3D visualizations to enhance high-resolution site characterization investigations. And you can see on the screen here, there's one from a dry cleaner where we used a hydraulic profiling tool to identify the geology of the site, and then another one in a LIF investigation where we found a great deal of LNAPL blow-up clay unit near a spilled UST. First, a little bit about myself. I'm a geologist and senior project manager at Terracon and a 2005 graduate from the University of Illinois with a bachelor's in geology and some advanced coursework in GIS. I've been doing this for over 15 years, and I specialize in creating 3D conceptual site models to assess complex sites. I've done this in over 150 investigation projects, including a couple in Australia and South Africa and Brazil. And I've also had a couple of these models published in a peer-reviewed textbook that you can see there. So some of the topics that we'll talk about today, sort of the growth of this HRSC or high-resolution site characterization industry, and also how the 3D visualization industry is also growing. Why HRSC data is suited for a 3D visualization. A couple example 3D visuals, basically just some case studies. And then a discussion on how these deliverables can be made for these projects and sort of the pros and the cons of them, because those are the questions I get asked quite a bit. And then finally, just some advanced data analytics that we could perform on 3D models once they're made. So first, the growth of the HRSC and 3D visualization industry. Before I get into the numbers, I just wanted to point out a few projects here. In the upper left is cone penetrometer test data. In the top portion there is an electrical resistance heating remediation project. That's sort of a before and after where we calculated how much contamination was removed. On the right there on the top is a membrane interface probe investigation, which we'll talk about quite a bit, the MIP technology. The bottom left is another MIP project at a dry cleaner where we delineated chlorinated solvents. And then the bottom there is a petroleum site where we found a lot of LNAPL below that gray clay unit underneath that in that sand. So I don't have the data for the entire industry, obviously, on how much this is being used. And I don't even have really all the data from our company. But what I do have is the projects that I've worked on over the past 10 or 15 years. And you can see there, there's been quite a bit of growth as of late. Basically, the last 3 years, it's doubled each year, and obviously we still have about a month and a half left of 2021. So I fully expect that we'll double that number from 2020 this year. So you can see this is just being used a lot more on sites, and it's not just HRSC, but it's also 3D visualization. And why is that? That's sort of the next topic is why is this HRSC data suited for 3D visualization? And first and foremost, the data is standardized. There's not a whole lot of companies that make the tools to collect this sort of HRSC data. The three big ones are GeoProbe, who makes the MIP technology and the HPT tool, Dakota Technologies for their LIF tools, and then Fugro with their geologic tools like this cone penetrometer test data. Now, because there's so few players here, the data comes in a very standardized format, which means you can automate some of this stuff using things like Visual Basic in Excel. I use Earth Volumetric Studio to model everything in 3 dimensions, and they have integrated Python scripting language into it. So essentially, you can write some pretty basic Python scripts to help you build these 3D models very quickly, and then export them as a deliverable and do it quite rapidly. A lot of times, smaller projects are turned around in 24 to 48 hours. And then finally, data density. Now, this is a little counterintuitive because these high-resolution site characterizations performed by MIP technology and LIF tools and CPT data, they generate tens of thousands of data points. And here's an example picture of that. And the reason why it actually is easier is that the models have to honor this data. And there's much fewer ways that you can honor the data when you have tens of thousands of data points. If you only have a few dozen data points spread out, there's different ways that they can connect, and your ISO concentration maps can look wildly different. But when you have thousands and thousands of data points, If you want to honor all of that data, there's just really only a few ways that it can be honored. So it's actually easier when you have this amount of data. So the first case study we'll get into is some membrane interface probe data. And this is a tool made by GeoProbe. And at this site, there was an underground storage tank that spilled chlorinated solvents, and we advanced 18 borings. And you can see right away in 2 dimensions where the source of the air, the plume was in purple, and then where it's migrating to the northwest there. But of course, we've got to look at it in 3 dimensions. And once we kind of turn it, we can see where that tank was and what those 2 plumes are. Essentially in orange, the MIP tool measures in voltage, so that the orange is 70,000 microvolts, and about 10 times less in yellow is the plume in groundwater. And then that fence there in blue and gray is actually the geology from the electrical conductivity sensor on the tool. And you can see it really mapped out the sand fill really well in the top 5 feet. And then we had some clayier soils and then some sandier soils down there at depth. So really you get a whole complete picture of your site, not just where the contamination is, but what also the geologic setting of the site is. This next site is actually from optical image profiler data, and this is a tool made by GeoProbe that basically investigates free-phase LNAPL from petroleum spills. And this was actually built from just 7 borings. And when I kind of rotate this, we'll just play this and see that we've got the UST is shown there in 3D. Those gray units are actually clay units from a hydraulic profiling tool, and we'll talk about more of that shortly. But we found a decent amount of free-phase gasoline on top of the water table there, but the vast majority of the contamination was actually found below that second clay layer, submerged. And why that is really interesting is we weren't expecting to find that contamination there. All the treatment at the site was sort of directed right at the groundwater table at 10 feet there by the UST, because intuitively that's where you find that LNAPL contamination. But we had reason to believe that there was a conduit made when they were excavating the UST, and sure enough, we found a lot of LNAPL contamination below that second clay layer. And the 3D model really shows that well. This next model is tar-specific green optical screening tool data, or short for TARGOST. And that's a tool made by Dakota Technologies, basically for heavier distillate types. And this is actually a manufactured gas plant. And these are usually a bit difficult to investigate because there's multiple types of distillates at these places, and they're a lot of times extremely old and multiple sources. You can see there the former gas holder at the bottom of the south there, and we actually had some some diesel tanks up there, diesel USTs in the north. And we'll show this. There was about 35 to 40 borings done, so we had tens of thousands of data points at this site. And we can see when we sort of look at it in 3 dimensions, we get a sense of where that contamination is. But even when you look at it like this, it's a little bit difficult. When you start connecting the dots, right now we're at 250% of the response emitter, and we're going to go down to 5. You can see how we have these 2 real big sources, a shallower one and a deeper one. So sometimes just connecting those data points, using statistics, the 3D modeling program, you really get a better picture of where the contamination is. Now you might be wondering why it sort of looks like that. And here's that same site, and here I've colored the distillate types 2 different colors. The one at the bottom there is actually extremely heavy distillate, and that's probably coal tar. And the yellow is heavier distillate, probably more like crude oil or degraded diesel fuel. And if you rotate this model, you'd see in the back there, there's quite a bit of middle distillate, which is likely diesel from UST tanks. And you could actually go on that link that you see right there. This is on a platform called Sketchfab, where you can yourself rotate this model, click on those numbers, and actually kind of take a tour of this site from your computer without needing to install any additional software. Clients really seem to like being able to manipulate their sites and see this data in this format. And that kind of leads me to the next phase of the presentation. But before that, I have one more site here that this really isn't any screening tool data like a MIP or a LIF, but I just wanted to show that you can do this 3D modeling with high density analytical data, whether it be soil or groundwater or even soil gas. This is actually a chrome plating facility where we collected over 250 soil samples and analyzed it for total chromium. And we'll just show what this looks like in 3D. Those are plating tanks and sumps. We're looking at it from a side view right now. We're going to rotate it up to a top view. It's difficult to tell where the contamination is until you connect the data points using statistics. And we're looking at everything above 420 milligrams per kilogram of chromium, which was the remediation objective at the site. And right away you could see, where we have superficial spills, how deep the contamination is, the footprint. And you could also calculate the volume of contaminated soil, which at this site above 420, it was over 4,600 cubic yards. And we actually excavated the soil at this site, and this model was instrumental in being able to figure out not only the locations, but the depths and the amounts and estimating for costs. So now, the next phase of our presentation, sort of the types of 3D deliverables that can be digitally delivered to you from one of these investigations, and the pros and the cons from them. So first and foremost are images. These are basically report-ready images like footprint maps, cross sections, or three-dimensional fence diagrams that you could essentially take a screenshot of this 3D model and use it in reports. The pros of this is these are very familiar. Everybody is familiar with these types of images, and they're really easy to create. The cons obviously are these are two-dimensional, and it's difficult to portray a three-dimensional model in a 2D image. So the next obvious solution is a 3D PDF, and this is exactly what it sounds like. It's an Adobe PDF that can be opened in Adobe Reader, and the model can be rotated freely by the user and zoomed in and out, and actually you could have different scenes as well. The pros of this is that just about everybody has Adobe. It comes standard on most computers, and the file size is also really small, usually about 5 megabytes or less, so they're really easy to transfer over any kind of email. The problem with it is the visual fidelity is a bit lower, and the viewer can lag, especially on larger models. So it's not my preferred method of transferring these models, but certainly some clients really like them, and it's universally available. The next is an interactive model that can be viewed either on Sketchfab, that website that I talked about before, or using a viewer by the 3D modeling software by CTech. The pros of this is that using the Sketchfab viewer, no software is needed. Essentially, you just need an internet address, and you could basically look at this model and rotate it, zoom in and out, and look at points of interest really easily. And that visual fidelity is phenomenal. Everything is extremely sharp, and much more so than the 3D PDFs. The problem with them, an internet connection is required, and you don't really get a tangible deliverable. You get an internet address that you can look at this model, and that might not cut it for some projects. I'd also like to say that internet address can be password protected, so that it's not available for anyone to use or see. Next is the 4DIM interactive model. This is a CTech product, basically the 3D modeling software product, and it's a rotatable model using a 4DIM viewer. This is my preferred method of viewing 3D models, because the pros are the visual fidelity is extremely high. They're easy to create and modify. You could actually write a Python script and create these 4DIMs, and if there's any modifications, you just have to modify the Python script a tiny bit, push a button, and it recreates it. And then you could take screenshots of it for images. So you basically have to make one 3D model, and you could make hundreds of images if you want. The problem with them is it requires the download of a free player from CTech's website. It's free, but this could be a non-starter for some people if they can't download the program, if they don't have administrative access. And the file size can be quite large on some models, over 25 megabytes, which used to be more of a problem, but nowadays with Dropbox, they go back and forth pretty easily. And then finally, animations, which are MP4 files. This is what you've seen throughout the presentation. They're essentially standalone 3D visuals playable with pretty much any media player. The pros are they're extremely easy to use. Basically, send them over, they hit play, and that's it. They're phenomenal marketing tools, also great for litigation purposes because they're so easy to use. The cons, which you can't see behind there, are that they are difficult to edit. If there's any slight changes, usually, if you want a rotation a little slower, you want to add a different piece of data, essentially you have to remake the animation. So that can get a little more pricey if you start having to remake the animation over and over again. But in a litigation setting, they've really proven their worth. Now the final part of the presentation, I want to get into some data analytics from this 3D model data, because the 3D models are really nice, they're great visuals, but there's all sorts of great data inside of those 3D models that we could analyze and really use to help not only delineate contamination and close data gaps, but also help design remediation systems. And that's the volumetric analysis that you can perform on these. You can figure out the distribution of the detector response by HBT injection pressure, which I'll talk about shortly. And then you could actually also perform a sort of a pseudo mass flux analysis with this type of data. So first, the volumetric analysis. Now here's another site. We're looking at it from a top-down view. And this is, again, membrane interface probe data. And this is the XSD sensor, so it's for chlorinated solvents. And right now we're looking at everything above 300,000 microvolts, and we could see right away, where the source, where the heaviest contamination is. And we'll play this, and we can see all the data points there in 3D, and we'll just start connecting the dots at different levels. Down at 250,000 microvolts right now. Going down to 200 and stop there, and then we'll start back up again. You can almost see how the contamination, spreads in the subsurface. It's really kind of neat looking at it this way. You can see kind of two superficial areas up there that are shallow and have some hits, likely sources. And then we'll bring it all the way back down to 300,000. So this in of itself, I think, is pretty neat, just to be able to see the response at all these different levels. But using this 3D modeling software, you could calculate the volumes at any level you want. And that's what I've done here and kind of shown it in graphical form. You've got XSD response at the bottom there on the x-axis. You've got the volume of impacted soil on the y. So you could sort of look at any response that you wanted. 300,000. We've got 178 cubic yards of impacted soil. If you want to go up to 50,000 at the response, you've got almost 11,000 cubic yards. And it's sometimes a bit difficult to calibrate and figure out the amount of contamination you have at each response level. This is actually low-level MIP data where you could regulate the flow of the carrier gas a little bit, and you have usually a much better correlation. But I think these types of sort of volumetric assessments can really help determine remedial costs really well. The next data analytical tool is being able to figure out the response distribution by the HBT injection pressure. So most of these tools now, most of the LIF tools and the MIP tool, also run what's called an hydraulic profiling tool. And what that is it injects a small amount of water into the subsurface as it's being advanced, and it's measuring the amount of pressure required to inject that water. So you could essentially figure out estimated hydraulic conductivities in the subsurface at extremely fine intervals. So what we're seeing here is in the blue there are really low injection pressures, which is you're likely in sand and gravels, which makes sense. You're at the ground surface where there's likely fill. And those gray areas are higher injection pressures, which likely correlate to clayey soils. And we'll play this animation. This is what's generally called a MI-HPT tool, a MIP combined with HPT. And you get this data all in one push. we could see right away that much of that contamination is in that sandier zone below the clay, which is expected. This was at a gas station. If we rotate the model, and we zoom in here, we could see though that in that area, there's definitely some response in that clay unit. But maybe we want to know how much. It's clear that much of the contamination is in the sand, but how much contamination is in that clay? And we could actually figure that out. We could just see what the distribution is by injection pressure. And what I've done here is I've binned it into 50 kilopascal range, the injection pressure, and then on the left there, on the y-axis, is the percentage of total response. If you add up all of these percentages, you'll get 100%. So we could actually see that the vast majority of the contamination is in those highly permeable soils with the lower injection pressures. And we can see though that there is some in those lower permeability soils, and those clays and those gray areas. So this is a really good way to sort of figure out if you have a left shift or a right shift. And if you have a left shift like we have here, you might be more applicable to do injections or soil vapor extraction or pump and treat. And if you have more contamination that's sort of right shifted into lower permeability soils, you might want to look at something like ERH or even in situ chemical oxidation with some soil mixing. So I think this can really help. It could be a really powerful tool for remedial design. It can help you figure out injection locations, injection pressures for sure. These could be obviously figured out as PSI, and you could figure out your injection pressures. And then, of course, for cost estimation, not only helping you figure out which remedial technology that you want, but how much contamination we're dealing with. But to finish with this animation, what we want to find now are locations that have higher injection pressure, so clay soils, but also high response. And those are them right there. Essentially, those are locations with a high response, above 3 million microvolts, and a high injection pressure, about 500 kilopascals, which is about 70 psi. So if we were wanting to figure out what we want to do with those soils, those are impacted clays, we might want to excavate those. We might want to use higher injection pressures in those locations, but this can really help target those, maybe those recalcitrant areas. And then finally, the last tool is a pseudo mass flux analysis, I like to call it. And essentially what we're looking at here is hydraulic profiling tool data, once again in side view from 6 borings. And we've got an estimated hydraulic connectivity here shown. You can see the blues are higher K units and the grays and blacks are lower Ks. And you could kind of see the units really well, but if you connect the dots, it makes a lot more sense. Basically, the blues correspond to sandier zones, the grays and blacks correspond to clayier zones. And now if we add in the chemical data, the XSD again, we can see where that contamination is located. And it's pretty easy to see where it is, but if you connect the dots again, there's our plume in the subsurface. Now we could stop here. If this is a source area, we might just be concerned about just getting that contamination right there. But if this is really far down gradient and we aren't concerned about removing the source area, we're just concerned about the off-site plume, we might be more concerned with how much contamination is migrating off-site and how we want to target that. And in that case, we might be more concerned about these high flow zones. What I've shown here in dark blue there are those zones that are above 20 feet per day. And those are where the groundwater is flowing faster, most likely. And if there's contamination in there, there's more mass moving through there. And what we could do is take this estimated K data and multiply it by the XSD data and get the pseudo mass flux analysis, which is shown here. Essentially, it's a unitless result because we're multiplying response in microvolts times an estimated K in feet per day. We don't really get a unit. But I think it's still really interesting to see that maybe the area to the left there's more mass moving through there because the groundwater is moving faster. So if we wanted to target a remedial technology or a slurry wall or a pump and treat system, we might want to not only be concerned about that one area, but also the area to the left there and get that whole plume. Now, just some final thoughts. I think HRSC technology I think is growing and all it sort of lends itself to the 3D technology. And I think both of these really reduce costs at sites. And the reason is, one, they build better conceptual site models. You get thousands of data points versus hundreds. You get more accurate installation of your monitoring wells. You're not just poking and hoping and that you're getting the most contamination. And you also close data gaps, which I know most people hate getting something back from the state or federal regulatory agency that you've got data gaps here and here, and these types of investigations can really help close those. But mostly they just help reduce costs, and that's because they could lead to fewer site mobilizations. You collect tens of thousands of data points in a day. You reduce the number of monitoring wells you need at a site, and I think this needs to get really the attention that it deserves. An HRSC investigation with a 3D model might cost $20,000 to $30,000. The cost of one monitoring well over its lifetime could be that. So if your HRSC investigation even helps you reduce the number of monitoring wells that you need at your site by just one or two, it really can help pay for the entire investigation over the lifetime of the project. So it really just takes just a little bit of foresight to see that these types of tools and technologies can really actually save money. And then, of course, you get improved remedial design. You could figure out where your contamination is, not only, and also the geologic setting of the site, so you could help determine the proper remedial technology, or maybe a combination of them. And then finally, to help support environmental litigations. We've done this on about a half a dozen sites, creating three-dimensional models, animations, even a sketchfab model that all the parties could use and rotate, and they've really gone over famously. So I can't stress how these models are really applicable for that. Well, I wanted to thank you for listening to me and hearing about HRSC and 3D technology. Please give me an email there at my address at Terracon if you have any questions, and have a good day. Thank you very much.